the final paper session of SummerSoc. And in the session we have 3 very interesting paper presentations. Each of them is scheduled for 20 minutes. And as for the previous paper presentations, we don't have time for questions, but you can ask all the questions in the poster session, which will take place tomorrow between 5 and 7. And our first speaker is Martin Sommer, and he will present a paper about an orchestrator for the dynamic extension of Automotive EE architectures to the cloud.
Okay. I'll try this one. Hello. So hello, my name is Martin Sommer. I'm from the Karlsruhe Institute of Technology, and this is the paper I wrote with my colleagues Hussein Zuma, Mark Schönewolf, and my professor Erik Sachs. And this is a completely different topic than we just had, so it's about automotive topics. And we will talk about cloud-based software components and an orchestrator, which is basically the central part of automotive cloud-based software components. So this is the agenda. I will define automotive cloud-based software components, and we'll go into the motivation for such things. We go into use cases, then the orchestrators discussed, and then we'll go into the concept and the typical implementation of such a thing. So what are automotive cloud-based software components? So as all of you guys know, so we have inside a vehicle, we have an EE architecture, which is based on many different electronic control units, ECUs. And these ECUs in the future might be connected to the cloud with a connectivity device and some cellular network, so they can actually be the vehicle can be connected to the cloud, and there can be functions executed there as well. So basically, cloud-based vehicle function or cloud-based software components are regulation, control, or monitoring tasks that are using the computing resources of the cloud and not the vehicle. And so they can get input from the cloud or the vehicle itself and replace functions that are currently being executed in the vehicle. So maybe some of you guys have seen this as well. This is the evolution of EE architecture. EE stands for electronic architectures. So basically where we are right now is here and somehow here. So we have distributed EE architectures with lots of electronic control units. So we have an electronic control unit for your windshield or for your door and all that stuff. And we are heading towards a centralization where the bigger control units are being created so that the smaller control units might be replaced in the future. And the future might look like this. So we have high-performance computers within the vehicle, which is something that's coming up right now, I think. Many companies are working on it. I think Bosch is working on it, and all those companies like Vector from Super, maybe you know them. And maybe in the future we have something that's called vehicle cloud computing, where we have functions that are actually not running in the vehicle anymore. This is what I'm talking about right now. What is the motivation of cloud-based vehicle software components? So right now you have a vehicle that's running out of a production line, and the hardware that is within the vehicle is constrained to when it was built. So as you know, the software is always increasing, basically increasing, and it will not be enough. I think the hardware will not be enough for the software that will be there for the life cycle of the vehicle. As a vehicle can have a life cycle of 20 years, and the software that it might need increases all the time. So maybe this is not possible anymore for the hardware, so it's maybe better to have the cloud as a resource for the execution of functions. Also another point, as we know, we are going to an electric future. it might be interesting to have functions like machine learning functions that are not executed in the vehicle but rather in the cloud. Because some, as you might have heard, like companies like Mercedes-Benz and all those companies are integrating huge GPU stacks of NVIDIA and all those companies in their vehicle. And they're actually going to need a lot of energy in the vehicle, which might reduce the range of the vehicle. So maybe in the future we have some of those tasks not running the vehicle but also in the cloud. And also, it might be interesting to reduce development costs. As you have a function in the cloud, it might be easier to access it and adapt it during lifetime. And another point that might be interesting too is you are able to create fleet data in the cloud and create machine learning functions based on many data that is collected by the vehicles. We have 4 different use cases for cloud-based software components, and one use case I'm focusing on is the control strategy, or as we call it, control over the air. So we want to try to close the control loop from the vehicle over the cloud back to the vehicle. And that's what I'm going to talk about. Now that we know this is our use case, we have to decide on the application model of the cloud-based software component. You might think of maybe just having a cloud-based function that is only in the cloud. The second use case could be that you have a fallback function, which means you have a component that is running in the cloud, which might be more smart than the fallback function. This is this use case. Then you have a duplicate application model, where actually it's the same software component in both cloud and the vehicle, but only one of which is being executed at the time. Then you have the parallel execution, which might be interesting in the future, as you might need safety critical functions to be redundant. So you can execute the same function in parallel at both locations and check the results and make it safe through that process. And you have the elastic thing where you are switching the location during the driving. So you're actually shifting the whole software component to the different locations all the time. So we had to decide which to take, and I'll talk about you later. So now that we know also the different application models of software, cloud-based software components, we need a central part, which is, I think most of you guys have heard of an orchestrator, which is basically the central part of a service-oriented architecture. And so in our group, we tried to figure out how to define such an orchestrator, and this definition we came up with basically based on the ISO standard for service-oriented architecture. So an orchestrator is a SOA module, SOA stands for service-oriented architecture, that oversees and directs the automatic selection and management of multiple resources and services in a dynamic environment to meet certain objectives. And these objectives could, among others, include time efficiency, consistency, security, and cost effectiveness. So we need such an orchestrator for our use case of control over the air. And so in our use case, we decided to implement such an orchestrator. And first of all, we decided to create lots of requirements, as we are in the automotive industry. This is the first step of the V model. And so it has to have an internal service database. It has to check the availability of each service. And the most important thing for us was it has to be able to establish a connection to an external network. So all those requirements went into the design of our orchestrator. And then we went to the use case. So we have the use case control over the air, but still not the real use case. And the real use case was the cloud-based heating, ventilation, and air conditioning, abbreviated with HVAC, control of an electric city bus. So we had a project with Daimler Buses located in Mannheim, and we analyzed the real-world data. Maybe you can see it in the back too. And we analyzed the real-world data, and we wanted to see how this data is distributed. So it was really interesting for us that the HVAC, which is here in red, can be actually have a more impact on the energy consumption than the drivetrain itself. which is where when you have a huge compartment in this electric city bus. So the HVAC is really having a huge impact. So we found our use case, which was we wanted to control the HVAC more intelligent than it is controlled right now, and we wanted to use the cloud, as we have more resources in the cloud, to create such a controller. So this is the one goal we wanted to do with such a use case, and the other one was maybe reduce the development costs of such a controller. The type of the application model we chose was the fallback application model. I forgot to say, so of course it's very cool for us that this HVAC thing is not a safety critical function in the vehicle, so which is also a reason why we chose the HVAC function, the HVAC control. So we went for a fallback function application model. So we will have an intelligent controller in the cloud and a fallback function in the vehicle. Maybe in the future we could think about having an only cloud application model. So you won't have a fallback. Maybe in the future with 6G or something, and you have lots of connectivity modules or something. So it might work in the future, only cloud. And we implemented the whole use case on our demonstrator platform, which is also called Atlas, just like the guys that just presented from Italy. And it looks like this. It's our institute. Here is the Institute für Technische Informationsverarbeitung. And we use this computer with the simulation environment Carla. Maybe you've heard of that too. It was developed, I think, in Barcelona, where you can actually use the Unreal Engine and drive a car around town, or have it driven automatically. And this is our EE architecture from the vehicle. We have a high-performance computer right here, and we have some small electronic control units here. It's TI boards for like braking and some easy stuff. And so the idea is to have this demonstrator for our use case, and we decided to have a service-oriented communication between all of those boards and the internet as well, the cloud computer, which is not shown on this picture. So we decided to go on the ROS2, Robot Operating System 2, as our service-oriented architecture. And we decided on developing a model predictive HVAC controller, which is going to be located in the cloud, and a fallback function of a PI controller. And this is how it looks then finally. So we have the cloud with the cloud-based model predictive control. And here on our up extreme, which is basically this, we have the fallback controller as a PI controller. And here is our orchestrator for finding, connecting, and starting the different services in the cloud and in the vehicle when connections lost or something like that. And here we have the Carla PC, which is this one, with the Carla simulation running and the cabin model, which is going to represent the actual compartment model of the city bus for representing the temperature in the city bus. This is how it looks in ROS2, with the orchestrator node right here, the simulation node right here, and the two different controllers here. And they're exchanging their messages via services or topics. And finally we evaluated our use case with this two graphs. So we have we wanted to see if the orchestrator is able to switch between the different execution locations, vehicle and cloud, based on the data rate it is measuring all the time. And we wanted to see if it is able to control the temperature within the vehicle. And we saw here there's huge drops in temperature within the vehicle, in the simulated vehicle. And that's because the outside temperature is at 10 degrees and we have door openings every now and then. So the temperature drops right here. But we also found out that the model we have implemented here for the compartment and the bus cabin is currently a machine learning model and has some issues. So we will maybe change that to an actual physical model in the future of the bus compartment. Yeah, so in the future we will talk about more the energy reduction potentials and maybe analyze the latency effects on the control performance. And that's basically it. This project, this paper was funded by the Softcar project. Maybe some of you have heard of it. Thank you very much. Any questions?
Thank you very much for the nice presentation. And exactly, questions will be, can be answered.